Areas between curves, volumes, also by revolution, using washers, discs, and cylinders. Questions? Yes, ma'am. But the other ones around, you don't see them from, I don't know. 6266. Okay. This is fairly similar to our triangle example in class. So what I've got is I've got a circle with some unknown, this means that this R is going to be throughout our problem. So I'm going to end up with R cubes and R squares and all sorts of other R values. My whole problem is going to be in terms of R. I think 67 works fairly similarly. So 67, the base of my solid is an ellipse nine x squared plus 4y squared equals 36. Cross sections perpendicular to the x-axis are isosceles right triangles with hypotenuse in the base. Okay, this problem is actually uglier than the one you're asked to do in 66 because the shape is harder. I'm dealing with the shape being a square in 66. I'm dealing with this weird shape here in 67. But let me see if I can figure out what this thing looks like first. The base of my shape in the XY plane is this curve. It tells me that's an ellipse. If X is 0, I get 4y squared equals 36. Or y squared equals 9. So y is plus or minus 3. If I set y equal to 0, I get 9x squared equals 36. So x squared is 4. So x is plus or minus 2. Now here's where I have to go back to pre-calc and say, I'm drawing an ellipse. An ellipse is an oval, and these are the vertices and the minor axis crossings. The longer ones are the vertices, the shorter ones are the minor axis. I'm going to draw a box. My ellipse lives inside this box, and it touches those 4 points and is tangent to the straight line curves that make up the side of this box. So when I draw this ellipse, it kind of looks like that. Now here's what I need you to picture. This part is flat in the xy plane, and my solid lives above this. Cross sections perpendicular to the x-axis. If I am perpendicular to the x-axis, I'm going this way. So when I cut this shape in a line perpendicular to the x-axis, and I pull this slice out, that slice is an isosceles right triangle. Isosceles right, what that? Right triangle has a right angle. Isosceles means two sides are the same. And when I think of a right triangle whose two sides are the same, they're the two sides that are on the right angle. So I have whatever this length is the same as this length, and there's my hypotenuse, right? It says the isosceles right triangle is the hypotenuse in the base. That means this is the hypotenuse. And the right angle is up here. So this line is this line. Okay. If I can figure out how long h is, the hypotenuse of my right triangle, I can go over here and I can figure out the area because I'll have a base and a height. And they'll be the same. So the area over here is 1/2 L times L. Base times height. But here's the L's in this version of the triangle. So now I go back over here. And I ask myself, to get from this point to this point, I need an equation for the top and an equation for the bottom. But the only thing I know about this ellipse is this equation. So how do I find the y value there? I only really need this equation. but I need to know what the y is. So let's take that equation and rearrange it to get y all alone. Divide by 4. 36 divided by 4 is 9. Minus 9/4 x squared. So when I get a plus and a minus and a square root. Which one's that y value? And this one? So if I want to know how far it is from there to there, what do I do with those two things? Okay, so that means that in this picture, h is the square root that's positive minus the square root that's negative. Yes? Which way are we adding up our slices? Which means I'm going to integrate from -2 to 2. Since my slices go this way, they're in terms of x. Means I should integrate in x. What happens here? So I get thing plus the same thing, which is 2 of them. So far, so good? Okay. Now I got to go back over here. Because I got to figure out what L is. Oh, that's a really bad version. I want these to be the same length. Let's try and make them the same length, Josh. There. If this is L and this is L, by Pythagoras, this is the square root of L squared plus L squared, right? Well, that's the square root of 2L squared, which is square root of 2 times the square root of L squared. So H is equal to the square root of 2L. That's H. To get L, I divide by the square root of 2, yes? Okay, so L equals H over root 2. The area of my funky triangle is 1/2 H over root 2 times H over root 2. Root 2 times root 2 times another 2. What's about to happen that's really, really nice? The square root cancels with the square. What happens to the 2? Which means it gets squared also. What's 2 squared? Which cancels with that 1/4, isn't it? This is my area in terms of X. The volume integral adds up all those slices, doesn't it? And you just told me where we start and end. I know how to do that integral. The difference between this one and the one you need to do in 66 is that this expression will have r in it, because we're using a circle whose radius is r, as opposed to this particular ellipse whose equation is exactly given. But I still know the equation for a circle, don't I? I just have to use r instead of, I think the one we did in class had a radius of 1. Jordan, is that better? Yeah. Okay. One of the larger issues at this point in calculus is learning to picture what these things look like. Now, I know that I could probably go to a generative AI and say, draw this picture, but I won't have that at an exam. I won't have that most of the time. I'm not jacked into the network. So I have to say, okay, I've got this ellipse. I've got these triangles sitting in it. Okay, they'll be small, they'll get bigger, they'll get smaller, but instead of being in a circle, they're in this narrower ellipse shape. Drawing that picture in my head took me quite a long time to figure out how to see that. So that's, to me, where this part comes into play. I need to be able to describe it and translate that description into a picture, and that picture into a set of equations. And I'm the first person to say, that's not easy. I was having a discussion, friend of mine, a couple weeks ago, because I saw a cartoon. Cartoon says, where do you fall on the apple test? That's all it says. But I'll give it to you in a different way. I want you to picture a ball. Picture whatever kind of ball you like. Put it in your hand. Hold the ball right now in front of you. You don't have it, do you? But can you feel it? Do you know what the surface feels like? Do you know what the color is? Are there seams on this ball? Is there a texture to it? How well can you picture this item? You know what a ball looks like. You're used to it. Now, throw it in the air and catch it. If you really know exactly what this ball feels like, you'll know how hard you throw it, how high it goes, and how long it takes to come back to your hand. And you're doing it intuitively if you've done the sort of tossing motion ever. You know that ball 100%. At some point, picturing something weird and abstractly described should become like picturing that. Psychologists actually say that there are people who have very vivid physical imaginations. Not only can they picture that ball, they can feel it on their fingertips. They can imagine the sound it makes when it hits the floor or hits the wall or hits another person. If you've had a dodgeball as a child, right? You have that image, all those sensory apparatus. And they're linked in a lot of people. And a lot of people, they aren't. And if you're a person who can't even see that ball in your hand, that you've held hundreds of times, doing this is going to be impossible. My goal is to bring you from, I don't know what this ball looks like, to, oh, there's no shape. But that's quite a stretch, isn't it? I am fortunate that in problem 66, they actually drew the shape for me. So I have the squares living above some circular base. And I see very small squares and they get bigger and then they get smaller again as we get to the back of the circle. So I can see this idea. And here's the one we did that was the triangles on a circle. All I did to this is I stretched it into an ellipse. More questions? Every year on the AP Calculus exam, there's a question like this. Every year. Here's a shape. Find its area. Now put a cross section that looks like something, a rectangle, a square, a triangle. Find the volume. It's there every year. For the past, well, for 14 of the past 16, 17 years that I've been involved with the project. Unless I'm grossly mistaken, that exam is today. Jordan, there's something sneakily nice about this integral. And I think it's the same thing that's going to happen in the integral you're going to do in 66. What power of x is on that 9? Ah, that's on the x, that's on the last term. What about the 9 itself? How many x's are there on that part? So that's x to the 0, right? And 0 and 2 are both even numbers. This is an even function. With our symmetry from chapter 5, I can actually say this is twice the integral from 0 to 2. And that'll make the integral easier to do because now one of the numbers I'm going to plug in is 0. Jack, as you can write, and that was an x to the first, I wouldn't be able to do this swap because then it wouldn't be even, because neither one would be odd, and it wouldn't be odd because one of them would be even. So they have to all be the same parity, same odd or evenness. And that prevents me from having to deal with the -2 raised to weird powers. And thus in 66 will have saved me from having the -r raised to weird powers. I've got 20 more minutes of time with your names on it. What other questions do you have? These assignments are due Wednesday. I'll see you then.